Can you all hear me?
Yes, we can.
Share the screen. This is the screen. This is the presentation mode. Can you see the slides? Let me
Not
get
yet, unfortunately.
Okay. See.
Now it's starting to share content. And we see the slides.
Good stuff. Now let me move, okay, the WebEx panel in the other screen so I can see whomever might have any question. All right. We have until 12:15, right, Edmund? I take it as a yes. Okay, so morning, everyone. Yeah, thank you. I'm Walter Riviera, AI technical lead for EMEA, and that means that I spend my days informing customers and partners about what we're doing in AI, either software and hardware, as well as provide first technical support to really play around with stuff, testing technology, deploying technology, and so on and so forth. Today, I'm here to talk about a current challenge, a good challenge. And I will start from this picture. This picture is basically represent the words. Oh, by the way, if you have any question, feel free to jump in anytime. I'm happy to stop every now and then and give a 10 seconds pause to see if anybody has some curiosity or some doubt that might want to ask, but feel free to interrupt anytime, no props at all. All right, this is the picture of the current world. So it pretty much summarized by data silos, followed by computing infrastructure. They are everywhere. And now the big challenge is, if we wanted to picture this, if we wanted to build a COVID-19 detection application, obviously, unfortunately, as you know, COVID comes up with different variants, right? So the ability to spot the different variants as soon as they come up and to share that knowledge with other countries that might not have been already affected by those new variants, it's critical. So in case we wanted to build a COVID-19 detection application with all the hospitals in the world, and I think that would be beneficial for everyone, right? This is probably what we would bump into. So those are hospitals with their own data silos, with their own computing facility. And we would need to centralize the data. So how would you practically train a model? I mean, let's think from this perspective. What we would need to make that COVID-19 detection application possible would be a model, possibly a deep learning model, that's sorted. We would need data. Again, that information is there. And computing facility, that's there as well. And eventually Intel can help with that. But how would you practically do that? Would you clone all the data from all the hospitals in one gigantic location? Who would be the owner for that location? Who would be responsible for that location? Well, you would realize that even if you get that far, and even if you identify somebody to be the new responsible, there is another kind of roadblock that comes way before getting to that point, which is represented by the data regulations, because all that information is legally protected by the HIPAA in the US, GDPR in Europe, and they are sensitive information. You cannot just copy and paste. You need to have approval, and even when you have it, because of these regulations, you cannot really move that data outside the venue, the facility where it was collected. So this is a very important point, right? Because then how do you solve that problem? And if you really think about that COVID-19 detection application, you can easily expand that over to Alzheimer's disease, over to Parkinson's disease, any type of disease. I mean, having access to a vast data sources for tackling the same task would be absolutely beneficial to make the model more robust, more able to generalize. But because of data regulation, that doesn't seem possible. So the big question mark is, how can we build the COVID-19 detection application? Does anybody have any insights? That's a question from me to you. All right. Well, the answer is federated learning. It's a standard. I'm going to show you basically. Right now, it's been adopted in healthcare, but also in financial institutions, manufacturing, and media. If you think about, I just gave you an example with COVID-19, but if you think about retail with all the customers, think about, I don't know, some of those companies that have some of those brands that have facilities in different countries. Think about banks. You might have the same brand in the US, in Europe, in different parts of Europe, in Asia, in Africa as well, or the same way apply for the retail, right? So all of them might benefit from collating their data together. Great example is just Intel. We have offices everywhere on the planet and in the biggest city of each big country. If we wanted to build, I don't know, something internal like a chatbot on the Q&A that employees at Intel ask to, I don't know, the internal platform, and we wanted to build a consolidated model, language model, we would bump into the same problem of sharing the data outside the country where those data were collected. So, for example, the office, the lab we have in Rome, I'm based in Italy, can eventually collaborate with the facilities in Milan. The offices we have in Munich can collaborate with the other offices in Germany, but not really going farther than that. So federated learning can be applied in multiple market segment, not only in the healthcare. But what is federated learning? Well, in a nutshell, just to give you a high level idea that can be easily understood, federated learning solves the data access problem, meaning you have multiple data owners. Okay, let's stick with the COVID example. So you have a hospital, for example, in Germany, a hospital, for example, in Italy, and a hospital, for example, in New York. And each one of them has their own data set because they have their own patients. So if they wanted to collaborate on training a model on such a data sets that they have, in the federated learning, what would shape is the paradigm, is how you orchestrate the whole process. So you can think of having two type of ingredients, components, the data owner, so we can call them collaborator, and one component which is called the aggregator. This aggregator is exactly the same as this. It's just overlapping. So let's say the three hospitals we mentioned before, hospital in Italy, in Germany, and in Munich, Milan, and New York would like to give birth to a federation. They would the manager from the hospitals would do the handshaking, all the bureaucracy, yada yada yada, and then the ball would move into the data scientist. So each one would allocate their own data scientist team to serve this purpose. So the data scientists would do some online meetings, some virtual calls, and then they would come up with a model that is suitable for solving the task they want to solve. When the all orchestration starts, the aggregator, which is just a process, is a Python process, okay? It can be hosted in any of the three or into an external machine. But in that case, it would clone the model off to each participant. Each participant would then train the model locally using the local data sets. And every now and then, at the end of every n iteration, and that n can be a parameter that you set, they will share the model back to the aggregator. Because the model is exactly the same, the aggregator, as the name suggests, aggregates them. So it's just fuse them together. It's merging them. And then the whole process restart. So there are obviously clever way of doing this aggregation. Instead of the standard average, the Fed AVG. Because if some hospital is providing you 10,000 samples of a certain disease and another one is giving you 200 samples, perhaps giving them the same importance by flattening the average might not be the most clever way of considering the contributions from each one. But there are more complex fusion functions, but you got the point. If this was too technical, let me give you another example. It's like myself and two of you are super passionate about AI, and we live in 3 different parts of the world. Again, I'm in Italy, somebody might be in Germany, somebody else may be in Spain, and we find out that on a given date, there is a Spanish, German, and Italian guru in AI delivering a special lecture, which is a once in a life kind of opportunity. And of course, because we are all passionate about the topic, we would like to attend all of them. But there are two unfortunate circumstances. The first one is that, unfortunately, the 3 professors, without even talking to each other, decided that the lecture will be held exactly at the same time of the same day. And it's a one-off. So if you attend one, you cannot go and attend the other. And the other constraint is that the content of the lecture cannot be shared outside that class. So it doesn't even work that I take the Italian lecture and then I share all the slides and all the content and the books with the other 2 people, and vice versa, because that's not allowed by law. So what we come up with is an idea that consists in having a shared Google document or something online where I take notes, and every now and then, let's say every 5 minutes, I copy my notes over that shared document, and the other 2 would do the same. So at the end of a 2 hours lecture, each of us, myself and the other 2 people, will have access to a 6-hour worth of notes. 2 hours coming from me that I attended the session in Italy from the Italian professor, 2 hours coming from the person that attended the lecture from the Spanish professor, and 2 hours coming from the person that attended the German professor. Now, what is important to notice is that at the end of the 2 hours, all the participants will have access not to the original content. So that rule was never broken. What was shared was only the learning of each one of us. So I didn't share the original slides. I just shared what I've learned, what I got away from it. So that's completely legit. And one might argue, well, but Walter, the way you take notes is different from the way the person in Spain and German might take notes. So it's not actually the same learning. While that is true for the example I gave you, it doesn't apply when we go back into the digital world, because in that case, the model would be exactly the same. So somehow the digital brain that is taking notes would be exactly the same brain. So that's why the learning would hold. All right. This is one of the biggest difference between federated learning and what we've been used to do so far. So far, if you think about a big HPC, the high performance computing centers, they have massive supercomputers composed by multiple servers. And in those situations, what would be the normal practice? Is to take your data onto the big supercomputer and then compute it whatever you want it to. So you would centralize the data. So what would move would be the data. Now, because of the data regulations, the data stays exactly where they are supposed to be staying, so where they were collected. The only thing that travels in and out are the models. As you can see here, the model A, B, and C, and then it repeated again. This is extremely powerful because if you think about the relevancy that all the data and information as a source of knowledge has been gaining because of the AI and because of the regulation, I think this is just mind-blowing, because we are redesigning infrastructure of the future based on this thing, and it's absolutely mental. I love this thing. Now, one might be concerned, hey, but Walter, do we have convergency? Because you're splitting, but it doesn't necessarily mean that mathematically the whole thing is still going to converge to something meaningful. Well, we did publish a paper on this when we firstly introduced the FedAVG concept. As you can see here on the blue line up here corresponds to the CDS, centralized data set. FL is the dotted green line, which is federated learning. As you can see, the convergency, we can get to convergency right after. It takes less to get up here with the blue lines, with the centralized, than it take with the federated. But ultimately, we can get to the pretty much same level. Obviously, this was an initial investigation. Now we find out that we can make the model even way more robust, so with better performances. But if you're interested in the federated learning concept, please be aware that the way you aggregate the data, so what is the aggregation function, heavily impact this, and there is a green area of research on this, because it's most of the things are yet to be discovered, in my opinion, because it's relatively new, and it doesn't automatically, as it's in general with deep learning is a non-convex space of solution, so nobody can guarantee you that you will converge. But in federated learning, that adds a level of complexity. Now, you've understood what is federated learning as a concept. You've understood that it helps us tackling the data access problem, so we can access information with at the same time being compliant with the regulations in place. If you like this, how can you make this happen, right? Let's say when we finish this session in 20 minutes, and you wanted to walk home and it's like, oh yeah, that was cool, I want to try out and build a federation. How would you practically do that? Well, a good way could be using OpenFL. This is a tool that we published last year. It's completely free. There's no license attached to that. It's on GitHub, and it allows you to orchestrate a federation exactly in the way I explained. So you can scale up to multiple machines, or if you don't have a cluster you can use, you can simulate federation within your own single machine. So in that case, it would just be different processes being spin up on the same machine. You can do that manually. You can do that with some bash script. And there is already an example of bash script that does that in the GitHub. You can work from Jupyter, and that supports all of this. So if you have a code that you've written, like what I used to call a monolithic code. Monolithic means you have one file where you start with the data loading, data cleaning, preprocessing, you define the data loader, and then model loading, a model definition with all the training and testing routines definition, and then you kick off the process. If you have that code with all of it in one big file, you can port that into a federation by leveraging some of the templates that are already available on GitHub. You got plenty of examples like from MNIST, involving TensorFlow, PyTorch, from CNN to RNN, all pretty much all type. And you can use those templates as an example to start and customize. You would realize that with OpenFL, you can also simulate those situations where the different institutions are getting data set from different distributions. So each one might require a different data pre-processing. For example, let's say we want to build the COVID-19 that takes in radiographies. Maybe one hospital is using a machinery from a brand, and another one is using a machinery from another brand. And so the images at the beginning don't come with the same size, same resolution, same information. So what you might want to do is to customize the pre-processing of each one, and make sure that the federation is compliant. You can do that. I'm happy to show you on the GitHub a couple of examples, but all of this to say that all the standard choices, so Keras, TensorFlow, PyTorch, code in Python, and you can also Dockerize the whole thing. So you spin up one Docker either as aggregator or as collaborator, and you can still have it at work. That's all available for you for free today. And there are also a couple of interesting publications and collaboration that were born out of these efforts. The most famous one are listed here, but there are many others. In Italy, I'm working with the University of Turin as well, and a couple of customers, and the University of Pisa. The University of Pisa, you are using this for the testing of the 5 and 6G connectivity efforts for European projects, for autonomous driving cars. And University of Turin, we are testing this on fraud detections and enhancing the algorithm on data set with the diverse distributions. But everything started off with the collaboration with the University of Pennsylvania. They created the first and largest federation of the healthcare institution alongside with us, and that was a publication that we released this year. Let me deep dive a little bit. This is exactly what I was talking about. This is it's a 2022 publication. You can find that online. But basically, we managed to create a collaboration of what we think it is today, as to the best of our knowledge, the world largest federation ever built, involving 71 institutions across the globe. So it was all healthcare institutions. We were working on a tumor segmentation, and that choice was mainly driven because of the availability of data. That was common ground, let's say, fairly populated with all the institutions. And as you can see, in Africa, we had more than one institution. So having a solid base of data to leverage is absolutely critical. It was an interesting experience, and I can tell you the most challenging part of this experience was to actually coordinate the human aspects of it, because when you start a federation, there is at the beginning, and you will see if you start in playing around with the OpenFL tool. OpenFL is also announced with privacy and security kind of features, so that you can actually build a secure federation. And part of that pipeline, I include at the beginning the certificate exchange. It's like officializing the handshaking. So each participant that actually takes part to the federation was allowed to take part. To do that at the beginning, right at the beginning, even before kicking off the experiment, there is a phase where the institution would basically exchange certificates. So that takes some backward and forward. You can, of course, if you're working on your single machine, you can skip all of it. So just for practicality. And you can also skip all of it if you're working with your own, let's say, VPN, right? But for a distributed environment, that is kind of encouraged. And coordinating this backward and forward with 71 institutions was a bit of a trick, but ultimately we got till the end and we published the results. The initiative that University of Pennsylvania is directly responsible for is the FATS. So that is a toolkit that allows you to work inside out of the tumor segmentation. FATS, the baseline of FATS is that the training process happens through a federated approach, and this is why we're here together. But there are many other components of FATS that can be retrieved in the University of Pennsylvania. And building on top of that, we started off 21 and also 22, the two challenges with a grant as a prize, where everybody can take part of to the challenge. It was also published on Kaggle. If you're willing to have a look at it because this fascinates you, it was the FATS challenge. There you have the GitHub with the solutions of the two challenges. And basically, the challenge was articulated in two main tasks. The first one was working on the aggregation function. The other one was working on the data split and data distribution. So really interesting stuff, and that's all available for you. Another very cool project was with NASA. So with the Frontier Lab Development Lab, basically in this case, the idea was to leverage federated learning to pull together different data sources. They wanted to somehow detect the physiological effects of the radiation exposure on the astronauts, but they didn't have too many information on the on such data, on such on real astronaut measurement. So they had to combine that with something coming from the lab on other experiments, and this was just a perfect way of doing it because they didn't have to move data outside of a sensitive area, and they could still make it happen. So this was really cool, and you have the article there. And now the bad news. So I told you what federated learning is, how you can make that happen yourself, but I need to tell you what are the cons, meaning federated learning solves a lot of the data access problem, but it doesn't protect the model, it doesn't protect the training, and doesn't completely protect the data. What do I mean? There are many types of attacks, but the two easiest one, the most famous one, let's say, just to give you the point, are the poisoning attacks and the extractions attacks. In the poisoning attacks, the ultimate goal of the attacker is to ruin your day. They just want to screw your day. They don't get anything. They just destroy your day. And sometimes this cannot be intentional, right? Sometimes it might happen. I'll give you an example in a few seconds. The extraction attack, the ultimate goal of the attacker is to steal data, is to steal information. How does it work? Well, in the poisoning attack, let me go back to this slide. In the poisoning attack, yes, here. Basically, if somebody breaks into the data owner B, for example, and I don't know, it's just shuffling the labels. What is COVID gets labeled as non-COVID and vice versa. That is basically screwing the learning on this model. As soon as the aggregator aggregates all of them together and it pushes it back, that poison will impact all of them. And since that model, aggregated model, will be cloned and sent over again, that poison will basically corrupt the whole federation. So because it's federated learning, one can easily enter, a malicious person is just enough is just happy to get into one of any of the collaborators involved in a federation to screw the whole thing up. So that's a big risk. In the extractions, we have a lot of communications here. We have the communication from the data owner back to the aggregator and from the aggregator to the data owner. So if somebody's sniffing that, especially on this side, somebody is sniffing this part of the network or this part of the network between the data owner B and the aggregator, or this one, and they can constantly sniff it from one iteration to the other. Basically, they can build up a system of equations and do reverse engineering to infer what were the data used to train that model on that local collaborator. That is bad. So how do we solve this? We find out that, in our opinion, to secure federated learning pipeline, you need three ingredients: confidentiality, execution integrity, and attestation. Confidentiality is basically protecting data and the models from the risk of exposure to untrusted party. Execution integrity is protecting the computation while it is going on, while this is happening, so at runtime. And attestation is validating that the software and the hardware are genuine. So if I'm the institution in Milan and I say, dear people in the federation, these are the list of IP addresses of my nodes that I want to use to train the federated model, somebody needs to tell, yes, it's actually Walter, and then those IP addresses are the actual one that he wanted to communicate. Nobody intercepted that email and added, another IP address or something like that, or is doing this on behalf of Walter. How do you do this? Well, we find out that software gets you to a certain limit. We started working on this secure technology that is on board on our latest generation of Xeon server, but it will also be available in the workstation and other CPUs that you carry on laptops. And it basically gives you a secure enclave. An enclave is basically, I like to think it as a garage, a secure garage within the memory, where everything that gets in there gets encrypted, but also at runtime. So you can protect stuff at runtime, and that is super helpful for hardware attacks. So if somebody's trying to sneak in while the training is going on, SGX can actually help you avoid to a certain extent, because you're never secure 100%, right? While we are projecting this on some other space in the world, somebody is thinking about the next type of attack, but this is absolutely a great ally. And you can containerize, you can put it into a virtual machine, the whole execution. Obviously, it comes with some overhead cost in the computation, but it depends on what is the trade-off. If we're talking with a bank or a hospital, this is absolutely fine, because the importance of the information they're holding, it's critical. So with SGX, we can actually hit all the boxes that we described before. This is a quick animation where we have two servers, and one server is hosting the aggregation and the collaborator, and each one is basically picking its own data. As you can see, it's doing the training within, you can see the blue shadow around, that means that the whole process is happening within the SGX. And how do you orchestrate the whole thing with SGX? You imagine you have a federation key, and that key, the encryption key, that encryption key is well known to all the validated machines taking part to the federation. So this node, let's say this one, which is only training and that's it, would access its own local data, would use to train the model within the SGX. Before leaving the SGX, it would encrypt, you see, it would lock the model with the federation key, and the same would do this one. When they meet in the aggregator would enter its own SGX, it would decrypt with the federation key, it would fuse them together, it will encrypt it again, and so on and so forth. The result of it is that the accuracy goes up. These are all the references. You will have access to this content, and these are some more additional content. And now let's open it up to questions. I saw before somebody had questions, but somebody has typed something in, but
There are 2 questions in the chat. I'm not quite sure if you can access it with the screen share.
yeah, I'm having, well, let me see, chat. Yeah. Okay. So I'm gonna read them. A model who could perfectly recreate the data distribution would be able to recreate samples from the training data. How does that not violate the rule that data may not be moved? That is correct. Probably that question was asked before I talked about this. So yes, the first premise is absolutely true. That is the extraction attacked. There are even other ways of attacking, like the backdoor. When you train a model with the, for example, with a marker, and every time the model recognizes that marker, it just switched the label. So there are multiple types, and you're absolutely right. And that violate the rule. The data might not be moved, but that violates also other rules, meaning that the person is attacking, right? So he's not doing something legit. But these are the ways you can secure. Other alternative ways to add security layer is to encrypt the whole thing. I mean, every time we buy something online, we are already having a backward and forward with our bank, with our credit card information on the web, but that still is happening on secure connection. So somehow there are ways. You don't have to worry too much about having uncovered areas, because as I said, SGX helps you locally to protect even at the hardware level. Encryption over the network is a good way to protect the information. So if somebody is sniffing it but don't have a decryption key, there's no much they can do. And there are other alternative ways like differential privacy, but and that's actually an alternative to federated learning itself. But that's actually a good input. Are you allowed to inspect the federated data? How can you trust that the federation data is not corrupt or mislabeled, for example? Hey, thank you for this question, because that's exactly the example I wanted to mention before. So let's go point by point. Are you allowed to inspect the federated data? Locally, I assume, because if you're not part of the federation, you cannot even ask for it. But let me be clear. If I'm part of a federation and I am the Milan hospital, I will not be able to access nor inspect the data from the Munich hospital or the Spanish hospital. Each one can only take care of its own local data. That's the first statement. How can you trust that the federated is not corrupt or mislabeled, for example? Correct. This is actually happened. This actually happened in the world largest federation that we built. In this example, what we found out, you can actually see that when you see the. So each single institution will perform a local validation. So you do training and then you validate locally. Then you aggregate the model and you do an aggregated validation. That aggregated validation basically tells you how good you're performing. Now, what we observed when we give birth to this world largest federation was that there was a hospital, specifically one, that every time we were aggregating that number to the big model, the performance were dropping. But interesting enough, locally it was good. So local validation was absolutely good. When it was aggregating, it was just killing the performance of all the aggregated model. And the long story short, it came up that after a few days and of head scratching and wondering, because at the beginning you don't even know which one is actually killing the performance. All you can see is, okay, this is the list of the 71 institution I'm working on, and this is the list of the 71 validation scores that each institution is providing. So they're all good. But when we collect them together, it just sucks. So starting from that, you can already understand how difficult it was to spot which one was actually killing the performances. So we had to aggregate, multiple times and finding which one was killing the whole thing. So then we reached out to the people in that institution. We asked, can you please have a look at what's going on there? Because this is what is happening. And we found out that instead of providing the brain tumor segmentation, brain images, they were providing the knees, the images. So that was basically killing the whole learning because it was another task. And once we found that out, we fixed that institution, we fixed that, and we had to restart the whole thing. But ultimately, the result was extremely encouraging. So going back to your point, how can you trust that the federated data is not corrupt? This is exactly, or mislabeled. This is exactly what happens. Sometimes the attacker is not a bad person. It's something that it just happens in the interaction because you have a lot of institution to talk to. So this stuff happens, but in that case, you need to go and see what was actually alarming us was that every time we were aggregating all the models, that the performance and the validation of the aggregated model was dropping. And so that's what gave us a hint that something was not working properly. But potentially, that you have very limited points to evaluate this. So you now probably appreciate the difficulty of this paradigm, the difficulty and the superpower. Can you give us some idea about the performance loss? In tower, probably that is 1208, so probably that refers to the SGX utilization, because I said it might comes with an overhead. It depends. It really highly depends. Right now, I'm investigating, for example. So last year, when we launched this technology, we did some benchmark initially. Unfortunately, I cannot disclose them because it was just internal investigation. I can tell you, we were struggling in scaling from one socket to 2 sockets. Then after investigating deeper, we found out that the kernel, some of the driver were not scaling properly with the SGX, because SGX was effectively launched last year, so it was pretty new. And so some of the Ubuntu out of the box or Linux out of the box driver were not supporting that properly. Now we changed that, and we actually contributed to add some piece of code to those kernels, and that problem went away. So now the scalability is high. The overhead is not too much. It's really not too much. But again, it depends how much IO bound is your code, how much compute bound is your code. Generally speaking, I would encourage to give this a go if you have that opportunity, because you can actually add a very good ally for the security perspective in a doable way. Because as I said before, an alternative could be considering differential privacy, like homomorphic encryption, but that is going to kill the performance because it's so compute intensive that federated learning with some secure adjustment might be the best option. So I cannot give you the idea simply because it's heavily workload dependent. If you're running a decision tree aggregation like we did with the University of Pisa, a decision tree, no problems at all, because it's standard machine learning. If you're running a shallow network, no problems. If you are running a BERT model or something like that, probably you need to investigate that, because there might be some need. And accelerators like GPUs or these fancy devices, unfortunately, don't have this secure technology. So there's a trade-off you need to balance out. And with that, I think I'm 1 minute off time, but hopefully I addressed all the questions. Feel free to reach out if you have any other curiosity. Those are my contacts, and the stage goes back to the organizer. Thanks, everyone.
Thank you, Walter, for a very educative session. And I hope the listeners really got a lot out of it. Might use the stuff, actually, all the presentations and all the material that we have presented for maybe future usage.